Hello everybody, welcome back. We have another concrete design video. This one's going to be on concrete failure and behavior. And the key takeaway for this video is how to design the amount of steel for a concrete member in flexure. Super crucial, super important concept. And there's a little bit of theory that goes along with it. But if you want to skip that part of the video, you can go right to the problem, check the timestamp in the comments. But what we're going to talk about before we hop into that is the phases that the member is going to go through and what defines our member based on the quantity of steel within it. So the first phase that we're going to be looking at is the elastic uncracked. This is pretty much the initial loading of the beam where our member is not going to experience any cracking yet. So that is going to be a very, very minimal load. Once we go past that initial loading, we're going to be entering the second phase, which is elastic cracked. All this means is that the stress created in this bottom tensile fiber is exceeding the rupture strength of the concrete. So that FR that we talked about in our first video on concrete design is being exceeded. So now there's cracks that are beginning to propagate, and the concrete area for those cracked segments should now be neglected, meaning that the steel is going to be responsible for taking that tensile strength. But an important point for this phase is that we are not yielding the steel yet. We're just simply having this concrete experience cracking before that yield occurs. But once we load our beam a little bit further, we're now entering that yielding phase. So that means that the steel has finally exceeded the yielding strain in the metal. So our steel is beginning to experience a yielding strain, but our concrete block up top is still holding strong. We're not experiencing enough stress inside of this block to completely destroy it yet, but we have yielded the steel. However, if we go beyond this, the failure loading is going to be met, and we're going to be experiencing failure, which is the final phase of our member. The concrete block is now going to be crushed. Our steel has already yielded, so the entire member is pretty much done. So that's kind of how the phase of concrete goes through its loading cycle. And we ideally design for this sequence of behavior, and that's because this is going to be a steel controlled failure, otherwise known as a properly reinforced failure. Why is that? This is because the concrete at the tensile face and the steel is going to give out before our concrete block is crushed. In other words, what this means is that this is a ductile failure and it's not sudden. So it gives engineers a bit of time to react to the visual signals of the concrete cracking. So this is ideally what we're looking for. We're looking for a steel controlled failure. But on the other hand, we could have a concrete controlled failure, which is very bad. And this is where the concrete is going to crush before any of our steel has yielded, meaning that the failure is going to be super sudden. And there's really nothing that can be done to have a visual indicator of this. So pretty much what's going to occur, your concrete's going to fail. The steel is going to be okay. But once this concrete gives out, who knows what's on top of it, what's being loaded on top. Very sudden failures are not good, period. So we're looking for a steel controlled failure. And how do we get this? Well, there's parameters that are controlling this, and this is based on your quantity of steel. So in steel controlled, you are going to be yielding the steel so that you first get this tensile breaking in your concrete before the crushing of this block. So you want to have a quantity of steel that is below a certain amount so that your steel is going to yield before everything crushes in the concrete, okay? Concrete control is the opposite pretty much. You have too much steel now, meaning that you're not going to exceed the yielding strain inside of your steel or the yield stress, and your concrete is going to give out first. All of it's going to be crushed. You're going to be left with some pretty good steel, but when you don't have this concrete medium preventing things from, collapsing through it, then that's not good, okay? So in summary, Steel controlled, you have less reinforcement, or you're under reinforced. Concrete controlled, you are over reinforced, which is very bad. In other words, as well, you have these reinforcing ratios that we talked about. We have the P, which is reinforcing ratio, and we have PB, and we haven't really touched on that yet, but PB is in between steel controlled and concrete controlled. So it gives us an idea of the threshold between the two. So the bad and the good, we know the threshold between them. So ideally, we figure out what the balance condition is and then design the quantity of steel below that in order to make sure that our beam is properly reinforced. And an effective way to do this is to use a ratio. We have C over D, which is equal to the strain or the max strain concrete over the max strain concrete plus the yield strain. Why is that? This is because of our similar triangle relationship we have previously talked about in other videos, that the strain developed in our member is going to be linear as you develop strain about the neutral axis. So we have 0 here, but whether you're in tension or compression, that strain is linearly developing. And if we know our max concrete strain, then we can interpolate where our yielding strain or the magnitude of the yielding strain based on these similar triangles. So that's all this ratio is really doing. What it allows us to do is it allows us to solve for either C or D and determine, most importantly, the C, which is where our neutral axis is going to be for that properly or balanced reinforced condition. And then we can interpolate where that properly reinforced quantity is going to be later on using our previously solved equations in other videos. And that's where we jump back into the problem. We talk about the balanced reinforced ratio, and we talk about moment resistance, and we talk about the area of steel required for this condition so that we have an idea of what we need to design for in a balance case, but more importantly, how to design for a steel controlled failure to use less steel than what's required in that balance condition. Okay, so let's take a look at this problem and see how we solve for these parameters here. Alrighty, so let's hop into this problem here. We have a reinforced concrete beam that has an effective depth of 400 mil, and it wants us to find the balanced area of reinforcement. It wants us to find the reinforced ratio, the balanced reinforced ratio, and the factor moment resistance. And it gives us the following parameters. And how do we begin with a problem like this? Well, we just talked about the balanced condition for the reinforced beam, which is right between over reinforced and under reinforced. And we have a relationship that we can use to determine what this is, or where the neutral axis is for this type of member. And it is dictated by this EY here. And we know that if you are balanced, your steel should be yielding. So that's going to equal to 0.02 for the steel. But to solve for that, or just to show you guys where that equation is coming from, you have 400 MPa, which is the yield strength of the steel, and then the modulus of elasticity of the steel. And solving that, you're going to be equaling 0.002 as the yield strain that develops. So now that we have that, we can actually use the C over D formula since we are given D, and we can solve for where that neutral axis is going to end up. And we remember what that C value is right here in this diagram. So let's go ahead and solve. So we have C over D is equal to 0.0035 over 0.0035 plus ES, or EY in our case, which is 0.002. We bring the D over, and we have C is equal to 0.64 times D. What's our D? It's 400. So we have 400 mil. Solving that, you're going to be left with about 255 millimeters. And obviously, if we wanted to turn this into an A value for our compression block, then we can do this formula up here. So A is going to equal to beta 1 times C. And beta 1 is going to be approximately 0.9 times 255, which is equal to 230 millimeters. Now, this 0.9 is obviously an approximate. This approximate generally works for FC prime between 25 to 40 MPa, right? So that's why I just went straight to that, okay? The next thing we should do, we should probably go ahead and start figuring out what this CR is and this TR. Since CR is equal to TR, we can then rearrange that formula in order to solve for unknown variables, which in our case is going to be what? The area of steel. So if we look at what CR is going to equal to, we have CR equal to alpha 1 times phi c FC prime AB. We have all of these nice little parameters already solved for, so we're just simply plugging them in. 0.65, 25, and then A, which is just solved for here, 230, and the B, which is at the base of our member, 400. This is MPa, so Newton millimeter squared, millimeter, millimeter. These cancel, we're left with Newton. So our CR is going to equal to 1196 times 10 to the 3, and that is Newton. We know that CR is going to equal to TR, so we can start rearranging this formula. If TR is equal to phi s Fy As, we can rearrange for that As value as follows. We have As is equal to CR on top over Fy phi s. And this is simply another plug and chug situation here, where we have the compressive force that we already solved for. That's in newtons, the 400 Newton per millimeter squared, and phi s, which is 0.85. Newtons are going to cancel. The millimeter squared comes to the top, and your As for a balanced condition is going to be approximately 3,500 millimeters squared. And if you wanted to find out how many bars we would need to fill this reinforcing arrangement, we can use a 25 m bar approximately, which area of the bar is approximately 500 mil squared. So if we wanted to know the quantity or the number of bars, it's simply going to be the As over the area of the bar. So that's going to equal to 3,500 over 500, which leaves us with about 7 bars. So that's your first answer for the area of steel required for the balance condition. Let's move on to the reinforced ratio for the balance condition and the moment resistance. All right, so now there's your answer for A. Let's go ahead and figure out what the balance reinforced ratio is. We know this formula. It's going to be AS over B times D. And we are simply plugging in, once again, very simple stuff. We have the area on top for balance condition, 400 for the B, and the D, once again, is given, another 400. That's going to equal to 0.022, which is approximately 2.2%, which is typically how engineers talk about how much reinforcement is within your member. So 2.2% of that total cross section is going to be accounted for by steel, right? And another rule of thumb, which I should have mentioned in the theory section, your balanced reinforced ratio is more like a design parameter. And typically the amount of steel you want inside of your member is going to be about 75% of what the balanced reinforcing ratio is telling you. Okay, so just keep that in mind for future design problems. And that's going to be your answer for number 2, or for part B. And then part C, we're asking for the moment resistance. We already know how to solve for this. It is a simple equation. Phi s As Fy D minus A over 2. You see the graph. You know how to do it now. We have 0.85 times the area of steel in the balance condition, millimeter squared. Fy is 400 because our steel is yielding. Let me write that in Newton millimeter squared. And we have D given 400 minus the A 230 over 2. And all that is millimeters. And then solving for this, you are simply left with a value of 339 kilonewtons per meter. And that's how you solve for the area of reinforcement in the balance condition. And I hope it gave you a little bit more insight on what we're looking for when we are designing a concrete beam. And I hope we really understand the difference between over-reinforced and under-reinforced. It is so critical and important when doing these problems. Alrighty, thank you for watching.